Okay, so welcome everybody to the One World Probability Seminar. So we're starting off again. So Pete and I take care of the organization this term, and we're going to have a bunch of talks every 2 weeks, roughly. And we're starting off with Alex Drewitz from the University of Cologne and Alexis Prevost from the University of Geneva, who will give talks about the near-critical behavior of a strongly correlated percolation model. So Alex, happy to go for happy to look forward to a talk.
Thanks, Dominic, for the introduction, and thanks to the organizers for having us. And apologies for the technical challenges that we were encountering. So, right. So we are going to talk about a percolation model, which is a bit non-standard in some sense, but it turns out that it does in fact exhibit quite a few very nice behaviors in terms of integrability and solvability. And the way we want to do so is by, first of all, in the first half of the talk, I'm going to give an introduction to, more standard models, such as, in particular, Bernoulli percolation. And then I'll gradually build up the model that we're actually interested in. And in the second part of the talk, it's then up to Alexis to delve into more details regarding one of the critical, or several of the critical exponents that we are investigating. And he'll also give some overview on proof strategies. So in case there's any questions, please don't hesitate to interrupt. So, to start off with, as I said, as a kind of more general motivation for a broader audience, we'll introduce Bernoulli percolation, Bernoulli bond percolation to be more precise in that setting. And this has been introduced about 80 years ago by chemists Flory and Stockmeyer, who were investigating gelation. So what you can think of here is, for example, if you're cooking an egg, then if you start off at the beginning, it's liquid, and then if you gradually increase the temperature, then in the 50s, in terms of Celsius, it somewhat starts coagulating, and so you see a polymer forming. So that's a very day-to-day example of gelation here. And it was later on then mathematically by Broadbent and Hammersley who introduced Bernoulli percolation mathematically while investigating gas masses for coal miners. So one of the reasons they came up with this model is because of its simplicity. So you can actually define it if you're on the Euclidean lattice, just by saying you choose for every bond that there is, nearest neighbor bonds, you choose them to be open with probability P and closed otherwise. And you do so in an IID fashion, which from a probabilistic point of view is the simplest thing you could do. And hopefully also, the easiest to investigate. But we'll see more on that later on. So, right, it then turns out that there is a non-trivial phase transition. So it means you do find a PC which is strictly between 0 and 1 in such a way that if you choose P smaller than PC, there only are bounded connected components of open bonds. Whereas if you increase P beyond PC, you actually see an unbounded connected and a unique one, in fact, forming. So here's a couple of simulations. It's obviously not ZD, but just a part of it. So you won't see a finite, infinite connected components, but what you can think of here alternatively is say, you try to go from the left part of this rectangle here to the right part just by using black bonds. So black here means open, right? So what we're seeing here is a simulation of, for each bond, flipping a coin that with a probability 0.4 is black and otherwise it's white. And then you try to find a black path going from the left boundary, say, to the right boundary. And no matter where you'll start at the left, you'll see that pretty soon you'll get stuck. So you don't find a connection of open bonds going from left to right here. And this is due to the fact that it's actually subcritical. So then what you can do is you can increase P and see how this behavior changes. So, yes. So this is P equal 1/2. And so if you now try to go from the left to the right part of this rectangle, it gets way more complicated to check whether or not you actually find a crossing. And the reason it's so complicated here is that P is actually, like this P equal 1/2 is the critical probability. So this is actually PC, and it's one of the few cases where you can actually compute the critical probability. Turns out at criticality, there is no infinite connected component. And then if you increase P even further, you see that there is a crossing from left to right. And it's also not so hard to find one, right? So here you see you're in the supercritical regime. And so this is like an illustration of the phase transition that's going on. Now, that is two-dimensional bond percolation. And this kind of percolation, also in its side percolation, where you talk about sides instead of bonds, has been intensively investigated. So by now, it has been reasonably well understood in the off-critical phases. For example, if you're here in the subcritical regime, that means you choose again P smaller than PC, you do have a sharp phase transition, which means that you have exponential decay of the probability of connecting the origin to the boundary of a ball of radius and just using black bonds or open bonds in that manner. So this is something that's decaying exponentially due to a famous result by Menshikov in 86 and also Eisenman and Nosky. And this implies that, in particular, once you're in the subcritical regime, you also have a finite expected cluster size just by summation. If you consider, for example, the cluster of the origin. So you look at the volume of the open cluster containing the origin, and then you compute its expectation. Also, if you're in the supercritical regime, so if you choose P between PC and 1, you do have a lot of results. So this slide by no means is complete or anything. It's just intended to show that these settings have been reasonably well investigated and also understood. For example, as I was mentioning on the fly before, the open infinite cluster is in fact unique. So that's Eisenman, Kasten-Newman, and Burton-Keen. We have chemical distance results. That means if you consider 2 points in your infinite open cluster, then you ask, what is the length of the shortest path using only open bonds to connect these 2 points? And it turns out that this length is called chemical distance. It's obviously lower bounded by the 1 distance, because that would just be the one you can, where every bond is open. And it turns out to be comparable to the Euclidean distance. And in a similar way as we had above over here for the cluster of the origin, you can also show that finite clusters in the supercritical regime have exponential decay. And okay, so I mean, these are just a couple of those properties which are known. And so it turns out that there's a lot of good reference. In fact, probably the most famous one among mathematicians is the book by Grimmett, which still is very much contains, at least regarding Bernoulli percolation, say in the non-planar case, most of what's been known. Certainly, there's also the book by Markus, Heinrich, and Remco van der Hofstad, in particular with an emphasis on higher dimensional settings. And so maybe as one takeaway, if you haven't looked at this book yet, Stauffer and Aharoni, but are interested in percolation, you might as well do so. These are actually, it's written by physicists, but I think it's a very good reading if you want to get some kind of understanding of the physics intuition that is behind the model, and which can also serve as an inspiration for proving new results. So Stauffer used to be a physicist here in Cologne. He passed away, unfortunately, but he did attend our probability seminars once in a while. So this was nice, but certainly independent of the fact that I'm mentioning him here. So here you also see further simulations, which have been produced by Alexis. So that's just what we have here is like a 3-dimensional box, side length 150 sides. And so if you see here, P is actually the probability that we had introduced before for opening, in this case, sides. And what's happening here is, okay, so the red one is the biggest one, the blue one is the second biggest one, cluster of open sides. And if you now slightly increase P, you see that there's actually something happening here. So you see that they are becoming more prevalent. And then once you're in the supercritical setting, that is 0.32, you see that the biggest one, that is the blue one here, is almost every. Yeah. And this is also consistent with simulations from physics. So they have shown that PC for three-dimensional side percolation is roughly 0.31. Okay, so again, you see that there is a phase transition happening here from very small clusters to large clusters. Okay, so when it comes to the critical or near critical behavior, the territory is in some sense way less charted. So most of what, or everything I've been talking about before, except for the simulations, was in the super or supercritical regime. Now, if you're asking what's happening at the critical point, or say close to that, things become way more complicated. So in 2D planar bond percolation, as I said before, PC is actually equal to 1/2. That's a result by Keston from 75. And Harris had been proving before that there is no percolation at PC. So this is a special case where you can actually compute these critical values. And if you're interested in sort of the near critical behavior of other observables, it turns out that they are expected to be characterized by so-called critical exponents, which are expected to describe the behavior of the system close to the critical point and at the critical point. So understanding a model at criticality somewhat amounts to understanding its critical exponents, and then you would call models that exhibit the same critical exponents as members of the same universality class. So one example would be if you consider Bernoulli percolation on certain specific two-dimensional lattices, such as the triangular lattice. You can actually, using SLE, so this powerful technique that has been explored about 25 years ago, starting, then you can actually consider this percolation function, that is the probability that we connect 0 with infinity just using open bonds. And it was Smirnov and Werner in 2001 who found out that it behaves like this over here. So that means 1/2 we know is the critical value. So what you see here actually is P minus PC. And you see that the percolation function behaves like a power of this quantity P minus PC. So this means that the critical exponent here for percolation is 5/36. And you can also compute other critical exponents in this specific setting, as well as in high dimensions. So Hara and Slate used the laser expansion, and then many people afterwards, to understand critical exponents in higher dimensions, so in particular in the mean field behavior. Now, if you were talking to physicists, they would actually tell you much more about these models. So, for example, there is the notion of a correlation length. So this is defined here as a P minus PC to a certain exponent. And one important thing here is that, first of all, it's a power law again, but you also see that P minus PC in that case will be, or like Xi will tend to infinity. So Xi in some sense is the natural length scale describing the length scale in your system. So if you're choosing P close to PC, Xi will go to infinity, and it sort of marks the threshold where if you have a look at a box of radius Xi, you observe, or say if you have a look at scale smaller than Xi, the system looks as if it was critical, whereas if you choose the system size larger, you see that you're actually not at the critical point, but still a little bit away from it, that is P minus PC. So in some sense, there's Xi is a natural length scale for that system. So for example, if you consider this, what I call here MRP, that is the maximum number of points that you find in a connected component inside a ball of radius R. So you look at the ball of radius R, say centered at the origin, and you ask, what's the biggest connected component of open bonds? I denote it by MRP, and then physicists conjecture that it behaves like R to the df, where df is the fractal dimension. This is strictly smaller than the ambient dimension d. Whereas if you go larger than psi, then you actually see that this, well, okay, this is a little bit. So I should have just put MRP here instead of intersecting, because MRP already is the number. But then it behaves like theta p RD, so it grows like the volume. And Alexis is going to tell you more about this in the second part of the talk regarding our specific model. So, but when it comes to math results or rigorous results, then, as many of you know, it's not even known whether theta of PC at the so that means the percolation function at the critical point vanishes or not. So it's expected to vanish, that is, theta PC should be 0. But this is unfortunately still a very open problem. Okay, so there's other percolation models which you might have heard about. I'm not going into details of any of this one except for the Gaussian free field here. It's just like to get you, if you have a different point of view and maybe you're more familiar with either Voronoi percolation or Boolean models. So there's a wide variety of models that people are investigating and have been investigating through the last couple of decades. And these models, they all have different subcritical and supercritical behavior. However, it's expected and argued by Weinberg-Halperin, that's a physics argument, that the universality classes of these models should actually just depend on the decay of correlations that you have in these models. So together with a master student, now PhD student at Imperial, of Pierre-François, together with Alexis, we've been able to confirm some of these models by percolation. In particular, the last 3 ones from a simulation point of view fall into the same universality class. And there is, in fact, one model in the above universality class of which we can say more. That means we can do rigorous, math and understand it more from a mathematical point of view. And in order to introduce this model, so it's somewhat a cousin of the Gaussian free field over here, well, we have to work a little bit. So, but I hope that by what I told you by now, I convinced you that it's actually worth to do this, because it gives you quite some insight into this model. All right, so to start with, I'll define the Gaussian free field. And the Gaussian free field, we can do it on a graph. So if you want to, you can just think of a ZD to make things easier. And you define simple random walk. So that is just choosing your neighbors uniformly and consider the corresponding Markov chain. And then you can define the centered Gaussian process, which has the Green's function as its covariance. So that's uniquely characterizing your Gaussian process in a little bit an abstract way, but that's certainly a neat way to introduce the Gaussian free field. So you can show that G is symmetric, positive, definite. So we can find such a centered Gaussian process. And one way to look at this is as follows. You can also say, if you want to have a look, say, at a finite subset of ZD, and you ask what's its density with respect to the product at back measure, you can write it like this. And this is one of the reasons why the Gaussian free field is sometimes also referred to as a d-dimensional analog of Brownian motion, where dimension now doesn't refer to the state space, but rather the parameter space. Okay, so here we look at, you see these Gaussian increments coming up here. And one property which very much sort of distinguishes this model from, say, Bernoulli percolation is the strong correlations that you have in the model, which a priori might deter you, but it turns out that they can be taken advantage of. So you see that the decay of the Green function is roughly like, essentially up to a constant, like the distance to the 2 minus d, if you take two faraway points in your model. So which a priori you think might complicate the setting, and in some ways it does, in some ways it doesn't. So here you see a realization of the 2D version of this Gaussian free field on a box with a 0 boundary condition. So the reason I chose this 2D is because it's easier to illustrate, but then that does not fulfill the assumptions on our underlying graph, as it's not transient. So that's why I had to put zero boundary conditions here, or lower for that matter. And what you already see here, and that might be as a glimpse of what's coming next, you have these black lines here, which are connecting your sites in ZD, right? Or like in the box in Z2. You see these, the black lines between neighboring vertices, and that will actually be quite helpful in the fall, later on in a little bit. But this is just like one way to get a Gaussian free field. And once you have the Gaussian free field, how do you get a percolation problem out of that? You can just ask, well, you consider the random subset of the underlying graph at which the value phi x of your Gaussian free field is at least h. So one way to see this is you can think of a hilly surface, and the surface height is given by phi x. And then you fill it up with water, or it's raining, and then you ask, what is the sort of set of connected components, or just the set of sites which are still dry, if you want to interpret it from this point. So certainly this is a model which has long-range correlations, and similar to PC, you can define this parameter h star. So here you have to get used to it a little bit, because the way you write it here is like, if you increase h, then the excursion set is getting smaller. So that's a bit sort of different from what you've seen for Bernoulli percolation, where you usually couple them in a monotonic increasing way. But other than that, that's just the same thing that happened before in Bernoulli. And this is due to Leibowitz and Saleur in '86. So they actually introduced the investigation of that model from a percolation point of view. And so then, just to name a couple of results, I won't talk about all of them. So 1 year later, it was Brigmont, Leibowitz, Maas, who showed that, in fact, this H star is positive for all dimensions larger than or equal to 3, and it's finite in 3 dimensions. Then Pierre-François Rodriguez with Alessandro Snitman showed that H is actually finite for all dimensions larger than or equal to 3. And it's positive, so strictly positive for D large. So the reason why strictly positive is, one of the reasons why strictly positivity is interesting here, is that you have a phase coexistence. So if you choose H close to the origin, close to 0, you percolate above H and below H. So in some sense, that's corresponding to a result of Campanino and Russo in Bernoulli percolation from, I think, '85, where they showed that PC is strictly smaller than 1/2. So it just means that density at the critical point is less than 1/2. So then together with Alexis and Pierre again, we were showing that it's actually strictly positive in all transient dimensions. And it looks here like it was 6 years later on. It wasn't actually 6 years, but maybe 2. We looked at another parameter, which I'm not defining here, but the interest of that one is that it actually, using isomorphism theorems, also settles a conjecture of interlacements phase transitions, and not only in Euclidean geometry, but also more general geometries where we have a dimension larger than 2. So I'll come to that in a minute. Just saying that if you can show something for this GFF, then it also might have implications on yet another model, interlacements, which Alexis will define in the second part of the talk. Okay, so then very recently, the sharp phase transition has been shown for the GFF. So that's Dumesnil-Copin, Pierre-François, Severo, and Goswami. And also Stephen Moorhead found another way to prove this, and also find lower bounds on the percolation function close to PC, which translate into upper bounds for the critical exponent beta that we're gonna get to know in a couple of minutes. So some of the geometries that we can treat that I was talking about before was this, I said, larger than 2. So if you think of this Sierpinski triangle, this is just this thing over here, this prefractal, and then you take the Cartesian product with the Z. We take the product with the Z to get something transient. Then you get this thing here, which is sometimes also referred to as a Toblerone graph, in particular by people who spend some time in Switzerland, I guess. So, and this is certainly one geometry that falls into the setting that we were able to treat, but also this d-dimensional Sierpinski carpet in 3 dimensions where you take out these middle thirds. And these are geometries that we will also be able to treat later on, but we do formulate it in a slightly more general setup. But just to give you an impression of what things look like. So, okay, now we had a look at the GFF, that is this random surface, if you want, on the underlying graph G. G was discrete, right? So, as I was saying, it was, for example, ZD. Now, for reasons that become clearer later on, or on this slide already, but like its full power comes about peu à peu, I would say. It turns out to be useful to actually put in these black lines that I was referring to before in the 2D sketch of the GFF, right? So they were there in order to sort of make it clearer what the underlying graph looks like and how the surface, maybe let me just go back, right. Yeah, these black line segments here, I mean, here they help you in particular for understanding what the surface looks like, but actually now we'll just insert these black segments into our graph. So this way, we end up with what is called the metric graph G tilde. And that construction goes back to OWPS at least 40 years ago, but in terms of the GFF and related models, it was Titus Lupu who brought this back into business again, and quite powerful. So, as I said, G tilde is just obtained by adding these line segments here. And the way you then define the Gaussian free field, that is the metric graph Gaussian free field on this G tilde, is by saying, well, you already know what phi looks like on the vertices, on 2 neighboring vertices. And what you do in between is you just interpolate using a Brownian bridge going from phi x to phi y. So it will be something like this. And well, you get a sort of a continuous function indexed by the underlying vertex set G tilde now. And in some sense, you can say that brings in analysis. So there's various ways to see why this is actually a useful thing, but one thing which turns out to be quite useful and which I think is understandable at that point already is to say that if you don't know phi, but only phi squared, and if you knew it just on the discrete lattice, you would not be able to detect a sign change from one vertex to the other because the square is always positive, right? However, if you now have the entire thing on the cable system, you would know, well, if there is a sign change, then there has to be a 0 somewhere on this edge for this extended version of this Gaussian free field. Okay, another way to interpret this is to say, well, you first sample your field phi, and then you do this Brownian bridge, and then you say an edge is open if the entire Brownian bridge from phi x to phi y stays above a certain level h. Then if you look at Borodin, you see, well, that's exactly given by this value over here. And this way, you directly see that this is actually a bond percolation model with long-range correlations. So this way, you can open up bonds just induced by this discrete GFF, and then adding this additional sort of thinning of open edges. Okay, so as I said, it might not be entirely obvious why this is actually a nice model to look at. I mean, you can define it, but yeah, I mean, there's easier models to define, but maybe this is easier to investigate than some of the others. So what are we interested in? Well, the excursion set, so I tried to put a tilde here in order to distinguish from the previous discrete quantities. And I'm just not putting any other tildes here below except for h tilde, because these quantities will only consider them for the metric graph GFF and not for the original. So right before we had this E larger than or equal to H, which was just a random subset of G. Now we do the same thing for G tilde, that is for this continuum system. We consider the cluster of the origin, which is it's just the connected components. So we had seen before Bernoulli percolation, we had these open bonds. We have the same thing here, except for, I mean, some bonds might only be partially included. And we have a strong dependence, like when one bond is open, it also tells you about other bonds being open or not. You know more about the probabilities. We also have this, well, slightly reparameterized now percolation or rather non-percolation function, that is the probability that KH is actually bounded. And then you, as before, you can define the critical parameter. Now it's H tilde star. You can do it in this way here. So if you choose it H further down, then you see, okay, you start percolating, so you're not bounded almost surely anymore. And some of the observables that we will consider, and that will also come up in Alexis' talk in more detail, are the truncated radius function. So that's just the probability of connecting the origin to the boundary of the ball of radius n, intersected with KH being bounded. So this just excludes that you are in the infinite cluster, if there is one. And we also consider the truncated two-point function. So that's the probability of connecting 0 with x in the open bonds restricted to KH being bounded again. Right, so these are some of the observables that play a key role in what follows. And what we want to do is we want to investigate these and try to understand what's happening to them as we approach criticality, right? So similar as in Bernoulli percolation, you're interested, if you choose P close to PC, how does your system behave? We want to understand what happens if I choose H close to H tilde star, and how does my system behave, okay? So there has been previous work on these, on this model. So as I said, Titus Lupu was the first one who sort of reintroduced this into our community. And so he observed that actually at the critical point, as it turns out later, which is 0, but at 0, he can compute the probability that 0 is connected to x in a finite component. And you can just show that it's given by this thing over here. Essentially, there's only two possibilities, like either 0 is connected to x in the same cluster of open bonds, that is in the level set. And if you consider sign clusters of the level set, you can show that the signs are independent on different clusters. So therefore, either you're connected or you're not connected, and then it means that the sign here is independent of the sign here, and you can use this and show that actually this is the right formula to compute this. Okay, so there's a question regarding, I mentioned SLE, that is true. However, we consider transient graphs. So in particular, we have dimensions strictly larger than 2, for example, as the things that I was showing before, like this Toblerone graph. And so in that case, SLE and conformal invariance is only of limited use. So this is why we use different techniques over here. But I mean, it has of course been used for understanding the two-dimensional setup. So, okay, so this tells you, well, the probability of connecting 0 to x decays to 0 as 0 and x tend to, well, as x is going to infinity. So that in particular means that if you want to percolate, you have to have a look at the excursion sets above lower levels. So you have to increase your excursion set, the random subset of the underlying graph. And that means H tilde star has to be non-positive. So it has to be smaller than or equal to 0. And we don't percolate at the origin. There have also been previous works by John Ding and Matteo Wirth. They consider the case Z3 tilde, so well, Euclidean lattice with cable segments. And they showed that this psi function, which we had defined over here, right? So this was the probability of connecting the origin to the boundary of a ball. That decays roughly like r to the -1/2 with logarithmic corrections over here. And We'll come back to this later on. All right, so we know H tilde star is non-negative, non-positive. And in order to understand this a bit better, what we have to do is we have to introduce the capacity, which is crucial for understanding our model. And in some sense, so if you haven't seen capacity before, it's just a measure of the size of certain sets. In a way similar to the Lebesgue measure, but it doesn't give you the volume, but rather the visibility of a set for a walk or Brownian motion coming from infinity. So it's also related to electrostatic potential. So in some sense, there's various ways to interpret it. And one way to define it is as follows. If you have a subset of G, you can say the capacity of the subset K is given essentially up to dx here, which is the degree of x, as the sum of the escape probabilities of a random walk. So hk tilde is the escape, or is the event that the random walk never comes back to k. And okay, so what you can do here is you can sum these probabilities. You see, well, the only thing that really matters is x and the boundary, because otherwise you're already there in the next step. Okay, and then it turns out that, for example, if you consider balls of radius r, the capacity of a ball of radius r is growing like r to the d minus 2. So it's smaller than volume, also smaller than surface order, but still it's going to infinity, right? And this is, well, okay, this exponent, okay, maybe let's come to that later on. Okay, so now the first result that I want to give here is that we can actually give a precise formula for the density of this random variable cap kh. So kh was the cluster of the origin. Cap is the capacity of the cluster of the origin. So in some sense, this result tells you something about how the size of this cluster behaves. It's just not measured in terms of volume. It's measured in terms of capacity. And it turns out to be the right concept in this GFF business. Okay, so the density of this random variable, right, kh is random, is given by rho ht, as we have over here. And the important thing is, okay, I mean, you can have a look at how this actually behaves. Yeah, so we can compute this density rho h. And this already helps us to get the following. So using that, for example, if you're on Z3 or ZD in general, you can see that the capacity of a set is unbounded or infinite if and only if the set itself is unbounded. So therefore, if we want to talk about the percolation phase transition, we can ask, okay, what's happening to the capacity of this set? Where is that happening? And here it turns out that the non-percolation function is given by, well, this thing over here. So, okay, since I have these technical difficulties, I can't draw a sketch, but we know that, okay, so phi is the probability of phi 0 being smaller than t. Phi 0 is a standard, is a Gaussian. And from this thing here, we can actually already get that h tilde star is 0. And that at the critical point, theta is 1, but we had theta was the non-percolation probability. So that just means that at the critical point, we do not percolate, right? And now if you paid attention to what I was saying in Bernoulli percolation, it's quite remarkable here that, you know, I mean, we had this rather general setup. I wasn't putting anything. I mean, I said, okay, we want it to be transient, but otherwise I wasn't at this point saying much more. And we get that h tilde star is actually the canonical thing that you get. So that means that unless for certain examples, maybe let me do this here. So Alexis had been working on finding counterexamples, and there are certain trees, for example, where you can show that h tilde star is different from 0. But the canonical setting, that is in particular on any Euclidean lattice which is transient, you have that the critical parameter is computable, it's 0, and it's independent of the dimension. So that's also something that's still to be understood better, right? If you think of Bernoulli percolation, you know, I mean, people invested a lot of time investigating, you know, asymptotics as d goes to infinity. Here, it comes for free. So, okay. So this tells you also that phi is continuous, and we get that, right, phi of h, phi of 0 is 1, and so we see that the critical exponent beta, which is characterized as follows. So this is one of the exponents that describes your system close to the critical point that I was talking about before. This is equal to 1, right? We have this very explicit this very explicit result on this limit here. So in particular, it behaves linearly as h goes to 0. Okay, and in particular, this also shows that the critical exponent exists. I mean, usually showing the existence of the critical exponent is yet another, another big piece of work. I mean, in intermediate dimensions in Bernoulli, we don't have this, right? Because we don't know what's happening at the critical point. All right, so the standing assumptions that we'll use for the rest of the talk are, we do want volume growth to be regular. That means this is just like Z alpha, right? So if you're in Z alpha, well, usually you call it D, but people from graph business who are investigating heat kernel decay and similar things, they call it alpha. So we called it alpha, and at some point we regretted it, but I think there's no choice of parameters we haven't been regretting so far. So anyway, what we want is that the volume of balls of radius r behave like a polynomial order alpha, or power with power law with order alpha. We also want a green function decay, and that should be given by this thing over here. So again, if you think of Z alpha, we have that this alpha is the alpha, and nu is equal to alpha minus 2. That is, right, this is what I showed you before, how the green function is decaying. So you see it's distance to the 2 minus alpha. Alpha is larger than 2, so it's going to 0. And okay, so one reason why we chose this rather general setup is that it allows us to show that, in fact, what we get is sort of independent also from the very microscopic structure of the graph. These are all macroscopic properties. All right, so one thing, this here I wanted to present in a bit more detail. So what can we say in terms of critical exponents? So we can first of all say that we set psi of h equal to this thing over here. H tilde star is 0, so it's just absolute value of h to the negative 2 over nu being the thing from the green function. This plays the role of the correlation length. So this, if you're at a level h, which is close to 0, how far do you have to look in order to see that you're not at the critical level? Well, this is it. And the reason this is it is also manifested in the following theorem, which is mixing or combining, let's say, various results. I mean, they evolved gradually and cover different cases. And if you put them together, we can get the following. So, for example, if you look at this line over here, tau was the truncated two-point function. So the probability that at level h, or above level h, you connect 0 to x in a finite cluster. Okay, so I told you before that psi is measuring the correlation length, so the inherent length scale to the system. So that means that if 0 is close to x in the sense that the distance is smaller than the correlation length, it should roughly behave like being at criticality, which you see is this thing here and this thing, because the exponential terms in here don't kick in yet. If you have r much smaller than psi, you don't really notice the exponential terms here. However, once you choose r significantly larger than psi, you do see that the exponential terms here are taking over, and you see that you're in the subcritical regime or in the off-critical regime, and therefore this here is decaying stretched exponential. So this is general in the alpha nu assumptions that I put before. Here, this is what we could specialize in the case Z3. So, okay, if you take exponentials, you see that it sort of amounts to this thing over here, except for us being able now to get the precise constant in front of the r log r term over here. And this is also an indicator. So you see that it doesn't depend. I mean, it's rotationally symmetric. So therefore, what you expect is that whatever kind of scaling limit you get, it should be rotationally symmetric in, well, I mean, more general, but we get it in Z3 here. Also, let me mention that this is sort of one case where you can actually establish these predictions by Weinrieb and Halperin from the 80s, where they showed that, or where they were showing from a physics point of view, that the universality class, that is these critical exponents, should only depend on the decay of the correlations. So in our case, this is given by the correlation length exponent is given by 2/nu, and it turns out to be different from what is known for Bernoulli percolation. So you see that here you actually do have disorder relevance in the sense that the correlations do have an impact on the results. Okay. So here you find our results in a more compact, presentation. Okay, so these are the critical exponents. So as you've seen on the previous slide, we can sometimes do more than just the exponents, but also tell more about the precise probabilities. And so what is expected is that sometimes on rigorous grounds, sometimes not, that scaling relations or hyperscaling relations between these critical exponents are holding true. So it's not like these things are flowing around independently in space, but if you have one exponent or a couple of the exponent, it determines other exponents. And you see that over here, they are certainly overdetermined. So here, right here, you find the different exponents. So here I put a cheat sheet. I didn't introduce them all, but we've seen, for example, beta. And Alexis will have a closer look at the volume exponents that we will investigate. So he'll introduce them more rigorously in his part of the talk. But in one way or another, these critical exponents are describing the behavior of the system close to its critical point or at the critical point. And the red ones here are the ones that we can compute. You see below what is expected for Bernoulli percolation, but the reason I put it actually is, I mean, the important thing for Bernoulli is the approximate equal, because as I was saying before, you don't know. You do have simulations, but you don't know anything on the precise critical exponents. Whereas for this model, which a priori looks much harder than Bernoulli percolation, we can actually compute them. And well, we expect them to be universal in the sense that they, for example, also hold for the standard GFF and not the metric graph GFF. Okay, so let me make a couple of comments here. So I didn't put the range of validity here, but okay, so you see that if alpha is equal to 4, then nu is alpha minus 2, so it's equal to 2. So this is just the boundary case. We can also say something, but we put here nu should be larger than 0 and smaller than alpha over 2, where you certainly get logarithmic corrections. And okay, but in particular, the case Z3 is included in all these setups. And some of the exponents are also hold in general, so beta, eta, and kappa for that matter. Okay, so rho had recently been investigated also by Jian Ding and Tsai, so he's a PhD student. As I said before, what you see is that they only depend on alpha and nu, right? There's nothing about the local structure of this model that comes into play when you want to get the critical exponent. So that is also something that's postulated or conjectured on universality grounds. Should only matter what's happening on the large scale in your model. You also see that if you take, say, on the Euclidean lattice, you take alpha to 6 from below, you do see that these exponents do converge to the mean field values that you get for Bernoulli percolation. So from dimension 6 onwards, these ones should be the same again. Okay, there's also further results in that direction by Wendelin from 21. And again, Jian Ding and Tsai from 23 in that direction. Okay, so this is more or less what I have to say, and that I think I did okay time-wise. So thank you very much, and I hope you look forward to Alexis telling you more about this, in particular proof strategies and further valuable insights. So it certainly pays off to stay on board. This is what I can guarantee. Thank you very much.
Yeah, thanks, Alex, for a really nice talk. So before we go for the next talk, there's time for some questions. So please feel free to unmute yourself or use the chat if you have any questions.
We have a question in chat. Alex, if you want to have a look.
Yeah. Yeah, background motivation in physics. I think it's mostly just so in some sense, in a way similar, the Brownian motion plays a very important role for us in probability theory, as I was trying to make clear before. If you consider d-dimensional parameter space, then the canonical candidate to look at would not be the Brownian motion, but the Gaussian free field. So from that point of view, it's a very natural model. It's expected that many other models converge in the scaling limit to the GFF. So in that way, it's a kind of universal thing. And yeah, but other than that, I don't know if there's further intrinsically physical reasons for it.
We have another question in chat.
Yeah. Is there any mathematical reason to use mean field values? Use mean field values. So, okay. So, well, I mean, ideally, you want to understand your model everywhere, right? I mean, so that means below the upper critical dimension and also in the mean field case. So the techniques that we developed lend themselves in particular to low dimensions. So in particular, dimensions up to including 3 are very grateful in some sense, because there you can play around very nicely with the capacity. So in some sense, well, the capacity of a line segment in these dimensions is comparable to the capacity of a ball. And this you can take advantage of. So then, okay, as Alexis will point out in his part of the talk, if you want to consider other intermediate dimension, you have to do more. You have to work. You have to bring in new ideas. So that's certainly very interesting, I think. And okay, I mean, and then obviously it's also very interesting to understand the mean field behavior. So yeah, as I said here, there's impressive work by John Ding and his student. For us, it was mostly also, I mean, if you put it in context with Bernoulli, or what's known in Bernoulli calculation, we found it quite beautiful that there is actually a model, a non-trivial one, where you can say quite a lot about critical exponents and near critical behavior in these intermediate dimensions, which on the one hand are non-planar. So there's nothing like SLE or whatever that's giving you a boost. And on the other hand, are still below the upper critical dimension. So that's something that's usually pretty hard. And I'm not saying it's easy here, but at least it's doable. And yeah, but mean field is, I mean, anything is interesting about it.
Okay, so
Okay, any other questions? Perhaps outside of chat? No one seems to be unmuting themselves. Well, in that case, thank you, Alex.
Thank you.
And I guess time for Alexis to take over.
Okay, do I start directly?
Well, maybe
I
we
mean,
can
still
do like
have a few minutes, so you can
Okay,
prepare
okay.
your slides. And
All right.
I guess if anyone needs to take a toilet break, now's the time.
So does it work? Can you see it?
We see your mouse, we see your slides, yes.
Right.
And just a reminder for everyone, we are also streaming on YouTube, and it will be available after the fact there as well. So if you missed any part, you can always go back and watch it there. Perhaps while we were waiting, I have a quick question. Alex, earlier when you sort of introduced the, what did you call it, the metric?
Metric ref GFF or cable system GFF.
Yes, so that is, I guess, in some sense, a monotone thing, right? Because I guess if you percolate in the cable model, you also percolated in the original one, right?
If you percolate in the cable model, you also percolate in the original model. Exactly, yeah.
So all properties translate in this direction, that essentially the existence of it in the cable model implies the existence in the original?
I mean, depends on, no, I mean, like, for example, I mean, the critical exponents, we don't get them for the original one right now, right? I mean, there's a lot of specific properties of the system coming into play. But the hope, of course, is that at some point you would be able to show that it's, I mean, we don't expect anything fancy or anything surprising showing up when getting these results for the original GFF. But in that case, I mean, even H star is not known, right? I mean, you do have asymptotics, but yeah, it's not as nice as in the metric ref thing where you can just say it's always zero. So in fact, it's not. Yeah.
Basically, the problem is when you translate your results from like one supercritical phase on the metric graph to the supercritical phase on the discrete, is that on the discrete, even if you are close to the critical point on the metric graph, then you are far from the critical point in the discrete. And so you don't get near critical result, basically. You do get something, but it's less interesting.
Okay. Dominic, do you want to start us off for the next one?
Sure. So welcome back to part number 2. So I guess now we're going to hear, like as Alex announced, a bit more details, in particular on the proofs by Alexis Prevost. So Alexis, looking forward to your talk.
All right, thank you. So you see the top of my screen, right? Yeah, the title and so on. Yeah.
Yes.
Okay. So what I will focus on during the second part is a new paper that will appear soon on arXiv, where we study in particular the critical exponents which are associated to the volume of the connected component for the Gaussian Phi-Phi metric graphs. And so what we want to understand is the volume of the connected component at criticality. So criticality, remember, this was H star tilde equals 0, or near criticality, okay? And so there are, let's say, two main quantities to understand the volume of connected components that we will look at. The first one is this quantity here, which is the number of vertices in the connected component of the origin. So you fix a point, let's say the origin of your graph to simplify things, okay? And this KH, remember, this was the connected component of the origin above level H, right? And this just means you look at the cardinality of it. So just the number of points which are connected to the origin. So this is one quantity, which is just the size of a given component. And another quantity that I will consider is the size of the biggest component. So the biggest component in a ball, let's say. So you fix a ball, BR, so all my balls, they will always be centered around the origin. And I look at what is the largest cluster in this ball. Okay, and largest, I mean in terms of volume or in terms of cardinality, if you prefer. So it's the one with the most point, and I look at how many points does this cluster has, and I call this M. So this is the maximal size of a cluster in a ball of size R. Okay, so basically this tells you, the first one tells you like what is the size of a typical cluster, and the second one tells you what is the size of the biggest cluster. So this, if you understand these two quantities, you understood well the behavior of the volumes of the clusters for your metric graph Gaussian free field. And so let me introduce the critical exponents which are associated to these two quantities. So I will first focus on the critical point. So here I take h equals 0, which means for my model, I am at criticality, right? And then, so at criticality, as Alex mentioned, you know that your clusters are finite, okay? So your cardinality is finite almost surely, but then you can ask what is the probability that it is unexpectedly large. So it is larger than n, and n here is really large, okay? So if you were off critical, this would actually decay exponentially fast, but at criticality, this is actually expected to decay polynomially fast. And the exponent here of the main exponent of your polynomial is called 1 over delta usually. Okay, so delta is a critical exponent that you want to observe, and you can define it also rigorously in that way if you want. But I mean, it's not clear whether this limit exists, right? And we will see that it is the case, but a priori, it is a hard question to just prove that this probability decays polynomially fast for Bernoulli calculation, for instance. And the second critical exponent I want to mention is the one associated to this maximal size of a connected component, and this is the fractal dimension df. So Alex already introduced it. Let me just remind you, this is just, okay, I'm saying that my maximal cluster at criticality, it will have a size which is of order r to the df. Okay, and df here is my fractal dimension. So what this means is that my biggest cluster at criticality is a fractal with fractal dimension df. Okay, and if you were taking, let's say, if you were in the subcritical regime, so your clusters would be small, and actually in the subcritical regime, your biggest connected component will only increase logarithmically fast, whereas in the supercritical regime, then like a good proportion of your points will be in your largest connected component, which is just your infinite connected component in your ball, right? And then you would have just of order r to the d points in your connected component. And it's only at criticality that you have this intermediate regime where you can have a fractal dimension which is strictly between 0 and d, the dimension of the lattice, or the dimension of your graph in general. And finally, I will also quickly mention what happens near criticality. So here, let's just focus for simplicity on KH, okay? And I'm taking here this truncating volume. So I'm adding here the fact that my cardinality is finite, which I need to add if I'm in the supercritical, because if I'm in the supercritical regime, then this would be easy to have a cardinality larger than n if I didn't put this condition, because my cardinality could just be infinite with positive probability. So I'm adding this fact to prevent this phenomenon. And then what scaling theory is telling you is that typically this probability, so this is similar to what Alex showed for the two-point function, it should have a first term, which is the critical term, so which corresponds to the case h is equal to 0. So if you look above, this is exactly the term h is equal to 0. So when h is equal to 0, this is just the equation above, okay? But then when h is not equal to 0, you should have a correction, and this correction should win, basically. So this means that here I have some super polynomial function f. So this function, typically you can think of it as a stretch exponential. Okay, this is what it will be. It could depend a priori on whether h is positive or is negative, but in fact it will not depend on it for us. And this function, so if you forget about h, let's say you take just h a constant, you take h equal 1, okay, this means that as n goes to infinity, this probability decays basically as f, because it will beat this polynomial here, Okay, so this is just the asymptotic decay of your probability. But here you also have, if you want to understand more precisely the behavior of this function, you also need to understand how does this function depend on h. And scaling theory tells you that this should be like h to the tau up to some error times n. Okay, and so this means that if n is smaller than h to the minus tau, then this is just of constant order. And so this behaves exactly like this polynomial. And so this is exactly like if you were at criticality. Whereas if n h to the tau is much bigger than 1, then this function starts to beat the polynomial here. And then you start to see the effect where you are actually outside of criticality. Okay, so this is, if you want, the scale in terms of volume at which you exit criticality. That this is described by this exponent, tau here. Okay, so I have these three exponents, delta, df, and tau. And I can first show you a simulation of this. So here, what I'm showing you is the largest cluster in dimension 3. And I have a box of size 300. And here, h is equal to 0.4, so I am subcritical, okay? The critical parameter I remember is 0 here. And so I just have a small component. So this one is the largest connected component. And remember, the size of the largest connected component in terms of volume, this is what I call the quantity MRH, okay? And so for instance, for the moment, it's quite small compared to the dimension of the lattice. But if you increase, if you decrease your parameter, your largest connected components slowly increase, and then you reach criticality at some point. So you're at 0, and you start to see a macroscopic cluster. It's not yet giant. It doesn't take all of the space. It is really fractal-like, right? And in this case, you can compute, okay, what is the size of the largest connected component? In this case, it's of order 10 to the 6, which for r equal 300 is of the order r to the power 2.46. So in this simulation, this tells you that, okay, df should be of order 2.5. Or, well, you know, this is not exact because r is 300 is not so big, obviously. This is an asymptotic behavior, and we will see in a moment that this is the case, that actually df is indeed equal to 2.5. And if I keep decreasing my parameters, then I start, my cluster starts to take more and more space until basically most of your box is taken up by just one giant cluster. All right. So let me now state our main result that I will then comment on the proof later. And just as a reminder, right, on the parameterization here, these are still the same assumption as in Alex talk, that is that the size of a ball grows as r to the alpha, okay? And the green function should decay as the distance to the power minus nu. So these are my two parameters. If you want, on the d, you take alpha equal d and nu equal d minus 2, right? And I will add one more assumption on my graph that a priori seems quite a strong assumption, but we will see in a moment that it is verified, in fact, on many graphs, including ZD in no dimension. And this extra assumption is the following. I'm assuming that my one-arm function here, so this is the probability that the cluster of the origin has a diameter at least n, so it reaches the boundary of the ball of size n, right? So this probability is that my cluster of the origin reaches n should decay as n to the minus nu over 2 up to constant. Okay, actually here the lower bound this is no assumption because the lower bound is always true. This you can prove, but basically the upper bound is an assumption. And under this assumption, then you can find a precise bound on the tail of the critical cluster of the origin, and it should decrease as n to the minus nu over 2 alpha minus nu. And also on your largest cluster in a box at criticality. And this largest cluster is of order r to the alpha minus nu over 2 and up to constant. And basically, if you choose your constant here big enough and small enough, then you can make your probability as close to 1 as you want. Right? So it is really of order r to the alpha minus nu over 2, the first order. At least. So this answers the two first critical exponents, which are the exponent at criticality from the previous slide. And let me just now comment on, okay, when is assumption 1 satisfied, and hence one of these two next equations also satisfied. So the first graph on which this was showed, which are any graphs as above where mu is smaller than 1. And this is from our paper in 22. But recently, we showed that it was actually also true on Z3, okay, where mu is equal to 1. And also on other kind of graphs. So for instance, you can, I mean, there's a specific condition, but this condition is, for instance, satisfied on the graph that Alex presented, such as this 3D Sierpinski carpet, or this Toblerone graph, so this Sierpinski triangle times Z, right? And recently, Kai and Ding were also able to extend this to prove that this is true on ZD until dimension 5. Okay, so on ZD, this is basically, right, as Alex mentioned, this is true until the critical dimension D equals 6. And then in particular, these two equations here are also verified on ZD until dimension 6. So for simplicity, I will just focus on ZD now, just to be a bit more clear. And what the previous slide is basically telling you now, if you combine the previous slide with this result of Kai and Ding, is that the critical exponent delta is equal to d plus 2 over d minus 2, and the fractal dimension df is equal to d plus 2 over 2. And this was actually initially conjectured by Werner, this value of df until dimension 5. And there's a reason why we are able to do all of that only until dimension 5 is that in higher dimension, you have different critical exponents. So, for instance, Werner proved that df is equal to 4 and delta is equal. He proved one bond, sorry, on df. And Kai and Ding proves that delta is equal to 2 in dimension larger than 7. Okay, and Kai and Ding also obtained some result in dimension 6, and if you combine them all nicely and so on, so we do that in the paper, and add some extra argument, you can prove basically that in any dimension larger than 6, you have that delta is equal to 2 and df is equal to 4. Okay, and if you compare these two results, you can see that they match in dimension 6. So if you take d equals 6 here, you obtain exactly 2 and 4 respectively. Okay, so you really get these two critical exponents in any dimension, basically, yeah, by combining our result with previous results. And note that this critical exponent in higher dimension, here they are conjecturally the same as for Bernoulli. Conjecturally, because it is not known for Bernoulli, it is only known in high dimension. But in low dimension, here, in dimensions smaller than 5, these critical exponents are different from the one for Bernoulli, also conjecturally. But yeah. And finally, let me mention our off-critical result, or near-critical, more precisely, which says the following. So if I now look at my truncating volume of the origin, okay, then, as I explained before, this is supposed to be of the order the critical volume times some superpolynomial error. And in this case, the superpolynomial factor here is exactly of order exponential minus x to the power d minus 2 over d. Okay, so this is like a stretched exponential factor, and this is exponential d minus 2 over d. You can see that I see this exponential minus d minus 2 over d here both in the upper bound here and in the lower bound. So it is really the correct off-critical rate. And then you can ask what are the factor which are near critical. Okay, so when you can ask a dependency on h inside your exponential, and there we don't have matching bounds. So for the lower bound, you have an h to the d plus 2 over d minus 2, and for the upper bound, you have an h to the 2d over d minus 2. Okay, so this gives you some bounds on tau, which was the correct exponent here in your exponential. We expect actually that the lower bound here is correct, and that this one is sharp, and one should be able to prove a matching upper bound until dimension 5. But so far the upper bound doesn't match, but it is still an interesting upper bound because it is telling you that the correct exponential decay is exponential minus x to n to the power d minus 2 over d, and then you can wonder what is the correct factor in h here in front of your exponential. All right. So that's it for the results. So if there's no question, I will switch now to the strategy of the proof. And I will focus on the parameter df, because the parameter delta is more complicated, although the proofs share some similarities. And I will also only focus on the case of ZD, and in fact, I will focus first on Z3 only, for simplicity. And what I will do is I will give you two slides, one slide for the upper bound. So I want an upper bound and a lower bound on the largest connected component in a box, right? That's my goal now. And in this, and I will give you two slides, and in two slides, you will have the impression, okay, I'm done with the proof, but obviously there will be a problem, otherwise it will be too easy. And maybe to keep you awake, since this is already the second hour, you can think where am I saying something wrong in my two slides, and what more needs to be done. So let's start with the upper bound. Okay, so I want to get an upper bound on my largest connected component, and I will start with recalling these results from Lupus that Alex presented, which was the very first result that was ever proved on this Gaussian Fifi metric graph, almost, which is that the two-point function, so the two-point function is the probabilities that 0 and x are connected, and the probabilities that 0 and x are connected, you can rewrite this as the probability that x is in the cluster of the origin, okay, which is just what I've done here. And this, what Lupus tells you is that this is of the same order as the green function. So Alex had given like an explicit formula in terms of arcsinus of green function, so okay, if you forget about the explicit formula, the main order is that this is of the order of the green function. And the green function on ZD is of order the distance to the power 2 minus d. Okay. Now what I want to do is sum this over x in a ball. If I sum my probability here over x in my ball, what do I get? I get the average number of points which are in my cluster. Okay, and so I sum this bond, and I get a bond on the average number of points in my cluster of the origin, which is bounded by the sum of the distance to the power d minus 2 in my ball. And basically, typically, these distances are typically of order r. Okay, so here you get some factor r to the 2 minus d. How many points do you have in your ball? You have r to the d, so you're left with an r square, right? Okay, so now I have one bond, okay, on how many points do I have in a ball at criticality, okay? But what I want is not how many points do I have in one cluster, the cluster of the origin, but how many points do I have in the largest cluster, right? Not the cluster of the origin. So how do I do that? The trick is to use the Cauchy-Schwarz inequality. So I want to know, in average, how many points do I have in my largest cluster. I take the square of that, and by Cauchy-Schwarz, this is just smaller than the average square of my largest cluster size here. Okay, so this is just Cauchy-Schwarz. And then with the interest of having this square here inside my expectation is that I can bound this by this sum here. Okay, so let me explain this. What I'm looking at here is K0 of x. This is a cluster at criticality of the point x. So K0 was a cluster of the origin. Here I'm looking at the cluster of the point x. Okay, and let's say that x is in my largest cluster. If x is in my largest cluster, then this cardinality, by definition, this is just equal to MR0, right? But now, for each x in my largest cluster, this is equal to MR0. So, and how many x do I have in my largest cluster? Well, I have MR0 of them, right, by definition. And so here I'm adding MR0 times MR0, so I get here an MR0 square factor by just summing over the x which are in my largest cluster. And so what this means is that if I sum over all x in the ball, then I just add points. So this is just an upper bound. But it turns out that this is upper bound is a good upper bound. And so now that I've arrived at this bound here, what I see here is that, okay, I can use linearity of the expectation. I put my sum out, and I'm left with the average size of the cluster of x in the ball of radius r. But this is exactly what I've computed previously, right? I mean, I did it for the cluster of the origin, but you can do it for the cluster of x. It's exactly the same computation. And so this is of order r squared. My sum here gives me a factor r to the d, so I get a factor r to the d plus 2. Okay, And so here you already see that the average size of the largest cluster is of order R to the D plus 2 over 2, okay, which is exactly what DF was. DF was D plus 2 over 2. And you can use Markov inequality if you want to just re-get the result that I was presenting before, which is that the probability that MR0 is larger than a big constant times R to the D plus 2 over 2 is small. If you take this constant, T is larger. Okay? So this is for the upper bound. Now let's go to the lower bound. So for the lower bound, what I will do is use a strategy that was first used by Bolthausen, Deutsch, and Zeituni, and has been used several times since to study the level sets of the Gaussian phi field. And this strategy is a change of measure formula, which I present here. And this basically is some kind of entropy bound and comes from like a Cameron-Martin formula. I will not go into the detail. Let me just explain to you what this bound is telling you and why is it interesting for us. Basically, it is a bound that lets you relate the clusters of the Gaussian phi field at a certain level to the clusters of the Gaussian phi field at another level for any event that you like of your Gaussian field. But let's apply it for the event that we want here. We want a lower bound on our cluster of the origin. So let's look at that. I want to look at what is the probability, lower bound on the largest cluster. And I want to look at the probability that the largest cluster is of the order R to the D plus 2 over 2. Okay, and I want to show that this is constant, or at least, or this goes to 1, let's say, but let's say first show that it is at least constant. Okay. So I want to show that this is constant, and the change of measure formula is telling me that, okay, I'm allowed to replace my level 0 here by a negative level, which a priori helps me because it is easier to have large connected component above level minus A than above level 0. And A here is a parameter that you're free to choose. Okay. But of course, you cannot just do that for free. You pay some exponential cost here when you do this change, and this is the lower one. And your exponential cost, this is like of order A squared R to the D minus 2. Okay. And you have some constant here. This is exponential minus 1. And you again see here your probability, the same probability as was happening here at level minus 1. A. So, okay, what do we need now? Well, we want this to be constant. So to get this of constant order, we want this probability at level minus A to be constant. And then we want to choose the A correctly so that this exponential does not blow up. I mean, does not blow up to 0, does not go to 0. And so that this exponential is also constant. So I want this term here to also be constant and this probability to be constant. And then everything will be constant. I will just get a constant. Okay, that's the goal. So let's first focus on this probability here. I want to show that this probability is constant. So I want to know how many points do I have in my largest component at level now minus A instead of 0? Well, the advantage of being at level minus A is that at level minus A, you're supercritical, so you have an infinite connected component. And you can look, okay, I want to know how many points are in my largest connected component. Well, my largest connected component in the supercritical phase, this is my infinite connected component. And the probability that one point is in the infinite connected component, let's say X, this is the result that Alex was presenting, and he was presenting an even sharper result of that, is that this is of order A. So I just show the lower bound here because it's what we care, but this is actually sharp. So this is this result that beta is equal to 1 that he was presenting before. So this tells me what is the probability that a given point is in my infinite component. And now I do the same as before. I want to do like a first moment method, and I sum this in X in my ball. Okay, so if I sum this in for X in my ball of size R, what do I get? I get that the average number of points which are in my infinite connected component, this is of order A times R to the D. Okay, and then you're like, okay, all these points that are in my infinite connected component, in fact, I have only one infinite connected component by usual percolation argument. And since I have only one infinite connected component, they are all connected together, so they are all in one cluster inside my ball of radius R. And so I can lower bound the size of my largest connected component by the size of my infinite connected component in my ball. And so this is what I'm doing here by summing the previous formula in BR. all right. So this is telling me, so now I come back to my formula and I want my exponential to be constant. So for my exponential to be constant, I want that a squared r to the d minus 2 is also constant. And so I choose my a is free to choose, so let's choose a so that this is the case. So I take a equal r to the minus d minus 2 over 2, so that this is now constant. And then for this specific choice of a, what is my bound here? Okay, this a r to the d is actually exactly my factor r to the d plus 2 over 2 that I want to have. And so this tells me that in average, for this particular choice of a, I have, in fact, r to the d plus 2 over 2 point in my cluster at level minus a. And so I can use the second moment method, that I will not go into the details of that, but you can use the second moment method to show that actually with constant probability, you have at least as many points as your average. So, so this means that you have at least r to the d plus 2 over 2 points in your cluster at level minus a, in your largest cluster at level minus. And so now you can just combine everything that I've been saying. We get all the ingredients. This probability is now constant. I choose exactly my parameter a so that this is constant. This probability is the same. It's constant. I have constant everywhere. And so I have a constant probability that my largest cluster at level 0 is of order r to the d plus 2 over 2. Of course, this does not show that this converges to 1 if you change your constant c, and you need further argument to show that, but it's not very complicated, and I don't want to go into that. All right. So hopefully now you're a bit convinced by both proof, but as I was saying before, there's a problem. So does anyone see where the problem could be, or has any idea? Okay. So maybe let me give you a hint. Okay. Well, we never used here the fact that we were in low dimension. Okay, everything I said works in any dimension. And as I was saying before, the exponent df here, which here we just proved was equal to d plus 2 over 2, in high dimension, it has been proved that it was equal to 4. Okay, so this proof cannot work. In high dimension, at least, it cannot work. And in fact, the upper bound is no problem. The upper bound is always true. In high dimension, it's also true. It's just not sharp anymore. But the lower bound here cannot be true. So on this slide, there is a problem. And if nobody wants to intervene and tell me what the problem is, I can tell you that the problem is in this sentence here. So I'm claiming that I have uniqueness on the infinite connected component, which is true if I look at my infinite connected component on ZD, but is maybe not true if I restrict my component to a box. So because here I'm taking a very particular value of R. Okay, so R is like a to the minus 2 over d minus 2, and so R is not so big. Huh? A is small typically, and R is not too big. So I am like close to the critical lump. So at this scale, actually I'm almost critical. So if I'm almost critical at this scale, it's not clear if I have a unique connected component. And in fact, it is not the case in high dimension. So this is something that Werner showed, is that in dimension larger than 7, there are many disjoint clusters at criticality, so of order r to the d minus 6. Okay, so your picture, your critical picture in high dimension looks like this. You have many macroscopic clusters. So macroscopic here means radius larger than r, could also mean volume large. And I mean, it doesn't really look like this because this is a 2D picture. In reality, all your connected components here, they live in different dimensions of your space, right? You have to imagine. And in fact, you can show that this is still true if instead of looking at the critical cluster, you look at some near critical regime. So if you take this level A, as we did before, which is r to the minus d minus 2 over 2, then this is what your infinite connected component looks like at this scale R. Of course, it's unique. So it means that all your connected components, they will manage to connect together far away. Okay. But at this scale, you see many connected components. So you do have a r to the d points in your infinite connected component, but your infinite connected component, if I restrict it to be r, it is made of many components. many clusters. Okay, and so this is not, so I don't have A R to the D points in any of these clusters. In fact, I will have a further R4 points in any of these clusters, so I have much less points in high dimension, at least. So now we see basically what the problem is in high dimension, why the previous proof cannot work. So we want to show that in low dimension, we can avoid this problem. And that in fact, this kind of picture will not happen. So what this means is that what you want to show in low dimension is that your infinite connected component is connected at level R for this choice of R here. Okay, for this particular choice of R, that in fact, this never happens and you just have one connected component inside the ball. Okay. So, okay, what is the strategy for that? So here is where I need to call a friend, and this friend is called random entailment. And so random entailment, let me first define it and then tell you why this is useful, because at first it might seem that it will be something which has no link with what I've been saying before. So it is a simple process to define. It is just a set of doubly infinite simple random walk on your graph or on ZD if you want here. So what this means is that each of these green trajectory is just a random walk, okay, simple random walk. And doubly infinite just means that, okay, it is simple random walk both forward in time and backward in time, so it's a random walk on Z. And all these random walks are independent of one another, okay? And the only thing you need to know to understand the entailment set is how many such trajectories do I have? And the answer is that, well, this depends on a certain parameter U that you're free to choose, and then you will get a different set depending on the parameter U, okay? And it's a Poissonian number of trajectory with parameter U times the capacity of the ball. So this is the number of walks that hit the ball BR. And remember, as Alex says, the capacity of the ball is of order R to the D minus 2. So this means that you get, typically in a ball of size R, you get of order U R to the D minus 2 point. No, sorry, not point, trajectories. And they are all independent random walk trajectories. Okay, so this is the entailment. Now, what is the link with my Gaussian phi field on metric graph question? Well, the link is due in part so to Schnitzman, who was the first one to see the link between the two in 2012, but this was in the discrete. In the metric graph, this is due to Lupu. And then Schnitzman proved a more precise version of this isomorphism that I will now present. And we also extended it to more general graph later. And this isomorphism is telling you that you can relate your infinite connected component at level minus A to your entailment set. Okay, so remember, what we want is to understand this infinite cluster at level minus A, and this infinite cluster at level minus A, you want to show that it is connected in the box of size R for a specific choice of R. That's your goal. And now I will retranslate this question into an entailment question. And why can I do that? It's because my infinite connected component, it is like my entailment, but it is my entailment which is augmented. So around my entailment, I had what you see here, these red bubbles, okay? And what are these red bubbles? They are critical cluster of some independent Gaussian phi field. So remember, critical means phi positive, or here it's absolute value of phi positive, so it can be also phi negative. Phi negative and phi positive have the same law just by symmetry. You can look at negative or positive the same. And so I add all my critical cluster here of a Gaussian phi field that are hit by my entailment. So whenever my entailment hit a critical cluster, I add it here and I put it in red. And if I look at all this union of all my red cluster, this has exactly the same law as my infinite connected component, but now at level minus A. And what is A? Well, A is linked to your choice of your parameter for your entailment, so your parameter U, and in this case, you take U equal A squared over 2. Okay, this is the correct choice to get your infinite cluster above level minus A. So this is a representation via entailment of my cluster. Yeah.
Ask one question. So this union of clusters that you are looking at, these are all clusters of the same independent Gaussian free field?
Yes. I fix a Gaussian free field, I look at its clusters, and I look at which one are hit by my interlacement. And I put them right.
Will they always sort of be touching the way they appear to be touching in your image?
Yes, because either phi is positive or it's negative. So since these are, I took out all the clusters. Each point, it's either in a cluster of phi positive or phi negative, because phi is equal to 0 with probability 0.
It's on the category.
You're taking the absolute clusters. Okay, thank you.
Yes. I had both the cluster of phi being positive and the cluster of phi negative, so they are everywhere, in fact. But I just keep the ones that are hit by my interlacement.
Okay, thank you.
And so this is my picture. And now what's left to be shown is I want to show that this infinite connected component is connected in my ball here. Okay, so this is not the case here, right? My red clusters here, they are not connected, for instance, to my red cluster here. So I could still have in theory multiple connected components here for this set, but we have the interlacement now to help us. And more precisely, what we proved is that in dimension 3, and this is important, you can compute what is the probability of the event, which is called the local uniqueness event. So what is this local uniqueness event? This is the event that all your trajectories in your ball of size R here, they are all connected together. So maybe they are not connected together in the ball of size R because maybe sometimes they're very small here, right? Because they might just enter your box and exit it almost immediately. But okay, if I allow myself to take a ball of size 2R around it, then they are connected. So this very small trajectory is still connected to all the other one, but in a twice bigger box. Okay, so this is the event that I'm looking at. And the probability of this local uniqueness event, it goes to 1 as R goes to infinity, but the question is how fast does it go to 1? And the important thing here is that it goes to 1 with a factor which is exponential minus u r to the d minus 2 to the power of some constant. Okay, good. So how good is that for us is the question, right? Well, remember our choice, right? What we want for the isomorphism to be true is to take u equal a squared over 2. And then what we want as a scale for my change of measure formula for the exponential not to blow up is I wanted to take a to be equal to r to the power minus d minus 2 over 2. And it turns out that then the u here and the r to the d minus 2 here, they are both of order a squared. I mean, one is a squared, the other one is a to the minus 2. And so they cancel each other exactly here. Okay, and so if you allow yourself some additional constant in your choice of a, which you can allow yourself, you can make this exponential actually small. Okay, and so you can show that this probability is of constant order actually for the choice of parameter that we are interested in. So with constant parameter, your infinite cluster looks like that. Okay, inside the ball of size R, you might have multiple connected components, but if you allow yourself to look at 2R, which you can, then actually all your connected components, they connect together like that, okay, with constant probability, which is good enough for us. And so this avoids the problem in dimension 3. So why dimension 3, in a sense? Like, why wouldn't this be true in higher dimension? Well, intuitively, you know, 4 is a critical dimension for the intersection of random walks. Okay, so if you're in dimension smaller than 4, so let's say in dimension 3, then you know that 2 random walks, so 2 of your trajectory here, they will intersect each other with reasonable probability. But if you're above dimension 4, then it's possible for 2 random walks to avoid each other forever. Okay? And so, okay, what this means that in dimension 4, this is critical, so you might still have some hope and you might lose some logarithm here, and it's all doable up to logarithm. But in dimension 5, your walks, they will avoid each other. And so this actually becomes wrong, the result that I showed above in dimension 5. And so the strategy fails in higher dimension because of that. So basically what I'd say now finishes the proof up to further details, but in dimension 3, but in dimension 4 and 5, you need more because you cannot use this local uniqueness event for the interlacement. So what we are going to do is instead use a hub to connect everything together. So let me explain that. So remember first that what we assumed really was not that the dimension was smaller than 5. What we assumed is that we knew that the one-arm probability here, so the probability that the cluster of 0 reaches distance r, was decaying as the specific power r to the minus d minus 2 over 2. Okay, this was our assumption, and it turns out that this is proved by Kai and Ding that this is true until dimension 4. So why is this assumption interesting for us? It's interesting for the following reason. You need to look at the capacity of your cluster of the origin. So now, if I just look at the capacity of the cluster of the origin, right, let's say I want my capacity of the cluster of the origin to be of the same order as the capacity of the box. So this means that my cluster of the origin should be almost as big as the box in terms of capacity at least. Okay, so this probability that the capacity of the cluster of the origin is of the order of the capacity of the box, which is r to the d minus 2. This I know exactly what it is because, as Alex said, we have explicit law for we have explicit formula for the law of the capacity. So this we know it decays exactly as r to the minus d minus 2 over 2. Basically, this is always 1 over square root of what appears here. This is always true. But if I just look here at the capacity of the cluster of 0, I don't look at the capacity. What I want here is to have everything happen in my box of size r. I don't want my cluster to be giant and go very far away. Okay, I want to look at local level. So let's look at the same probability here, but inside my ball BR. Okay, so I restrict my cluster to the box, and then there's two possibilities. Either my cluster was anyway included in the box, so then this restriction intersection with BR changes nothing, so this is my first term here. Or my cluster was exiting the box, and this is my second term here. Right? So if my capacity is big, either I'm included, then this capacity intersection with BR is big, or here my cluster reaches the boundary of the box. But under this assumption, these two second probability, I can also estimate it. And it turns out that they are both exactly of the same order. And this is why I need this order here. This is my assumption is chosen so that here I have the same order for both. And okay, if I allow my constant t here to be small enough, okay, I change a little bit my constant t here in front, then this term here, this first term will be bigger than the second one, and so this whole thing will be of order r to the minus d minus 2 over 2. What this means is that inside my ball BR, I have not two small probabilities that the capacity of my cluster of the origin is of the same order as the capacity of the box, okay, which is this capacity. So this is this central hub here, okay. So, okay, the problem is that this is not with constant probability, but actually with a bit more work, what you can show is that this is good enough to prove that somewhere you will find a cluster in your box which has capacity r to the d minus 2. It might not be the cluster of the origin, but there will be a cluster somewhere. Okay, and so let's take this cluster here that I put in a bit more red than the other one, a bit more opacity. And this cluster, I consider it, and I only keep my interlacement trajectory that hit this hub. Okay, so I might have other interlacement trajectories in my infinite connected component, but I just disregard them. Okay, forget about them. And the point is, since this cluster, by construction, it is a cluster with a big capacity, with the same capacity as the capacity of the box, actually, I don't forget so many trajectories by doing this, because the capacity of this is large. So I might lose a proportion of them, okay, maybe half of them or something like that, but I just lose a constant proportion of them. Okay, so most of my trajectories are kept, and so now if I re-add all my all the other clusters as before that were hitting my trajectory, I still get a set which has the same cardinality as my infinite connected component up to constant. But what is the main interest of doing that is that now everything is connected at scale r. Why? Because everything is connected to the hub by definition. Like I only keep the green trajectory that touches the hub, and then two green trajectories that are connected inside the hub by definition, because it's one connected component. And then I just keep all my red clusters that were attached to my interlacement here, and they are connected to my interlacement. So everything is by definition now connected. And so I avoid the problems that I had in higher dimension, and this is thanks to this assumption here. So if you want, this assumption here this is characteristic of the low dimensional setting, and this assumption will not be verified in a higher dimension. In fact, this was proved by K-ending, and here you see the reason why it cannot be verified. And you could also just say, okay, another way to say it is that this existence of a hub, so of a critical cluster which has capacity of the same order of the ball is only possible below the critical dimension. And above the critical dimension, you will not have such a hub, and actually all your clusters will probably have capacity of order R⁴ or something like that. So that's how you can also adapt the proof in dimension 4 and 5. So, yeah. And that's it for me. Thank you.
Yeah, thanks a lot for a very nice talk. So are there any questions? So again, please either unmute or use the chat. Okay. Well, if not, maybe let me go ahead with the first question. So again, in terms of universality, so in principle, it looks like that everything you said should have like an somehow an analogous expression in all the other models, right? Or could it be the case that so maybe just like in terms of like the scaling relations, so to speak, could it be the case that somehow some of these constraints are like broken in some sense for some models, or is it really like, okay, whenever so whenever you say, okay, you have like this low dimensional behavior, that this should really be universal for like most of the models?
So let's say, let me give two answers. The first one is, if you really take a model that is like the Gaussian field on the cable system, on the metric graph, sorry, then it should be exactly the same. So this means that it's a model which is in the same graph, and that has the same decay of the correlation. So the correlation in your model decays as the distance to the power minus d minus 2. Exactly. Then you get the same things.
Okay.
If, then you might say, okay, what happens if now I look at over correlations? Okay, so I take another model, maybe just a Gaussian field, but not the Gaussian free field, which has this decay of correlation. So you're still on ZD, so it's not the green function anymore, but it's just your covariance kernel, okay, which will be decayed like that. Then you expect actually to have the same critical exponents as the ones that are basically here and here, okay? But then it is not like until dimension 5, you have always the same critical exponent, because the fact that these critical exponents stop being what they are at dimension 5 comes from the very specific 5 that nu was equal to d minus 2. And so actually, even in dimension 4, for instance, or 3, you could at some point reach the mean field regime if you reach a certain value of nu. So I think it's the barrier is then 2 nu equals 3 alpha, where you reach the mean field regime. So this will still be universal in the sense that for nu small, they will be true, but it's not like in dimension 3, this will always be the critical exponent. It will depend on how you choose nu, which was for us just fixed equal to d minus 2. This is what I expect, at least, to be true.
No, thanks. So I think
we have a question by Andrei.
Thank you. Thanks. So my question is just, you briefly mentioned this, it was a great talk both, but what is the exact specifics for dimensions 3, 4, and 5? Well, you briefly mentioned short explanation, but why is the situation so different than, say, 2 or 6 and higher? And maybe this is the question out of line, but could it be possible that the dimension is not an integer? Thanks.
Yeah, so, okay, why is the dimension smaller than 6 and larger than 6 so different? it's maybe a bit hard to just explain like that why is it exactly 6, let's say. Like what is true is that if you take your dimension high enough, then basically you will forget a bit about the geometry of the lattice, and basically your clusters, they will live on different parts of your lattice. Okay, and then they will just live into different dimensions, and you will basically look like you're on a tree. Okay? And if you look like you're on a tree, then actually your critical exponents are exactly this one on a tree. So in high dimension, this is what happened. You forget about the geometry of the lattice, and you clusters grow in different directions, basically as if they would be doing on a tree. And in low dimension, this is not anymore the case, and your clusters influence each other. They will come back to one another, and this is why you have these different behaviors. And it's a bit hard to see why 6 is the correct dimension. But yeah.
And does this has any, I mean, more intuitive explanation apart from just mathematical properties? Why 3, 4, and 5 for the metric graph GFF?
Well, why 3, 4, and 5? I'm not sure.
Yes.
Like the proof actually is quite involved to show that it's until dimension 5. It's clear that there is like a low dimensional regime and a high dimensional regime. Why is it exactly 3, 4, and 5 is maybe not. Maybe like what you can say is like in dimension 3, you see here for the argument here that this is like things work well thanks to like the intersection property of random walks, okay, which works well until dimension 4. And then, okay, why does it work in dimension 5 is a bit more involved, to be honest. And maybe to come back to the second part of your question, yes, you can take a non-integer dimension. And here, this is in fact the case. I mean, I didn't mention it, but the parameter alpha here, it can be any real, okay, I mean, larger than 2. So you can have anything here that you want. And in fact, there are graphs which verifies this for any value of alpha and nu that satisfies some reasonable assumption, etc.
And is then the analysis that you do holds for any number between 2 and 6 or 3 and 5? So
yeah, so that's
3.6.
No, it's a bit different on different graphs, and actually, this is what I was saying is that the actual condition, I think, which is true, but it's not proven, is that 2 alpha should be larger than 3 nu. Like if you take alpha equal d and nu equal d minus 2, then in dimension 6 you exactly have 2 alpha equal 3 nu. I mean, it's a simple computation, and so this is the actual limit where you start to change your parameters and they become mean field on general graphs. Yeah, but I mean, if you translate it on ZD, this is d equals 6, but it's just the formula is a bit more complicated on general graphs.
Thanks.
All right. Any more questions? Well, doesn't seem the case. So thanks again, Alex and Alexis, for very nice talks. And I think we'll continue in 2 weeks with talks by Balin Todt and Chris Lutzko. So see you in 2 weeks then.
Thank you for the invitation. See you.
Thanks for having us.
Thank you.